Hello and welcome to online lecture number 7 for Chemistry 1101 during the spring semester of 2020. In this lesson, we're going to continue on with chapter 9, which is all about solutions, their preparation, terminology, and ultimately their properties. We ended the last lesson looking at how the nature of the solute and the nature of the solvent will largely determine whether the solute is soluble or is insoluble in that particular solvent. We had the like dissolves like rule for molecular compounds and the solubility rules for ionic compounds. But there are other factors we might be able to change to affect the solubility, to either increase it or decrease it. And one of those factors, which is usually quite simple to change, is the temperature of the solution. And so if you take a look at this figure, which plots the solubility in grams of the substance per 100 milliliters of water as a function of temperature. And all of these substances in this graph are solid substances. And so what we can find is that generally speaking, with at least one notable exception here, but generally speaking, as you increase the temperature of the solution, the solubility of the solute in that solution increases. Sometimes it increases fairly slowly, but sometimes it increases very rapidly. So in general, what we can say, there are exceptions, but in general, we can say that the solubility of most solid solutes in water will increase with increase in temperature. So if you're trying to dissolve a solid substance in water and you're not able to dissolve enough of it, then generally speaking, you should be able to increase the temperature of that solution, and that therefore allow you to dissolve more of that substance in the same volume of water. If we take a look at a similar graph, but this time we're plotting solubility versus temperature of various gaseous substances. What we find here is largely the opposite trend as what we saw with solid solutes. With gaseous solutes, as we increase the temperature, the solubility actually decreases. So with most gaseous solutes, what we can say, generally speaking, is that their solubility decreases with increasing temperature. And one consequence of this, for most of us, our most common exposure to solutions composed of a gaseous solute, maybe our carbonated beverages, our sodas that we enjoy. And certainly if you're pouring a cold soda at really low temperature, the solubility of that dissolved carbon dioxide is relatively high, versus a warm soda, and when the temperature is higher, the solubility is less. So when you pour it out of the bottle, more of that carbon dioxide is going to come out more quickly. Therefore, you can get more foaming initially as that carbon dioxide tries to escape as quickly as possible. So we see that with temperature effects, it largely depends upon whether the particular solute is a solid or a gas. For solid solutes, as you increase the temperature, the solubility increases. With gaseous solutes, the reverse is true. As you increase the temperature, the solubility decreases. There's another factor, though, that will influence the solubility of gases, and that is the pressure for gaseous solutes. What we find is that the solubility of a gas, to what extent does that substance dissolve in water, will be proportional to the pressure of that gas above the water. So at higher pressure, that's going to essentially force more of those gaseous molecules into the liquid. Therefore, that's going to increase the amount of gas in the liquid, and then we can then quantitatively describe that as an increase in solubility of that gaseous substance in the liquid. So we can say, generally speaking, that the solubility of gaseous solutes in water will increase by increasing the pressure. So with gaseous solutes, if I want to increase their solubility, I can either decrease the temperature and or I can increase the pressure of that gas above the liquid. And as we saw with the ideal gas law, one way we can increase the pressure of the gas is by increasing the amount of gas above the liquid. And soda manufacturers, once again, take advantage of this. They know that most of us enjoy drinking the sodas because we like that bite that we get by drinking the soda. That bite is due chemically to the dissolved carbon dioxide in the soda. The more carbon dioxide that's dissolved in the soda, the more that bite. The reason why sodas go flat is because most of that carbon dioxide has left, and so you no longer have that same bite taste to it. And so when they can or bottle soda, they put the soda in there and they put a very, very high amount of pressure, additional carbon dioxide pressure in that small space between the liquid, the soda, and the top of the bottle or the top of the can. So as a result, the can is under really high pressure of carbon dioxide. Once we open the can, or open the bottle, get sound, which is due to the carbon dioxide escaping, that all that excess carbon dioxide is escaping. And as soon as that happens, the solubility of carbon dioxide in the soda will decrease. And then over time, the carbon dioxide will escape, and then the soda will lose a lot of its flavor. So those are some factors we can change to influence the solubility of substances in water: temperature and pressure. Now we get to the last part of this chapter, which is concerned with understanding the properties of these solutions. We want to understand the behavior of these solutions in the same way that we want to be able to understand the behavior of pure substances. We do that largely by the intermolecular forces and other structural effects, as we talked about before. We want to do the same thing with solutions, understand why they behave the way they do. Well, if a solution is composed of two components, at least two components, the solvent, the component in the greater amount, and the solute or solutes, the component or components in the lesser amounts, then the properties of the solution, properties of the whole, properties of the mixture, will depend upon both the identities of the solute as well as, and especially, the solvent, essentially what those substances actually are. But it also depends upon the composition of the solution. In other words, not only what the solute and solvent are, but also what ratio do we have between the solute and solvent, or solute and solution. And we call those ratios, those ways of expressing how much solute we have per solution or how much solute you have per solvent. We describe that as its concentration. And like any other property, we can describe it both qualitatively and quantitatively. So qualitatively, we might describe the concentration of a solution as being more concentrated or less concentrated. If we drink coffee, we might describe the concentration of a cup of coffee as a strong cup of coffee or a weak cup of coffee. And those are ways of describing the concentrations of those solutions. But the problem with these qualitative concentration descriptions, as well as all qualitative concentration descriptions, is that they're a little bit ambiguous as to their meaning. So if we say something is more concentrated, then the obvious next question is, well, more concentrated than what? Or if this cup of coffee is weak to you, it may be strong to someone else. So even though these are easy descriptions to make, we want to try to avoid them if at all possible. So largely, to best understand the properties of solutions, we want to use a description that has less ambiguity. And so therefore, those would be quantitative concentration descriptions. And there's a variety of ways of describing quantitatively the concentration of these solutions. We're only going to focus on two: percent concentration, and then chiefly on the second one called molarity. So with percent composition, we can actually define percent composition three different ways. And what we'll find is that even though they're defined three slightly different ways, what they all have in common, in fact, what all these concentration units that we'll talk about in this class have in common, is of describing the amount of the solute per amount of the solution. And with percent composition, the only difference is the units we're using to describe the amount of the solute and or the amount of the solution. So the most common way of defining percent composition is what's called the mass of solute, mass per volume, which is defined as the mass of solute per volume of solution, percent M over V. Sometimes you might see this as percent W over V, but it has the same meaning. And so this percent mass over volume is defined as simply the mass of the solute in grams per milliliters of solution times 100%. So that's our most common way of defining this percent composition. Another way of defining percent composition would be percent mass over mass. So this is a mass of solute per mass of solution, percent M over M, or sometimes percent W over W. Either way, it's defined as the grams of solute per grams of solution times 100%. And finally, we might encounter where both the volume of solute and the volume of solution are used. This is percent volume of volume. And this is especially relevant when the solutes are liquids or the gases are or the solutes are gases, because it's relatively easy to define or determine the volumes of liquids and the volumes of gases. So in this case, in a similar vein, this is defined as the milliliters of solute, volume unit, over milliliter solution, another volume unit, times 100%. So for our class, we're just going to want to recognize these and be able to calculate percent mass over volume, percent mass over mass, or percent volume, given how the solution was prepared. So an example of that might look like this, where we want to calculate the percent composition of a solution prepared by dissolving 8.46 grams sodium chloride in 175 milliliters of solution. So here we have our picture describing what's occurring. We dissolved 8.46 grams of sodium chloride in enough water for a total solution volume of 175 milliliters. And we're asked to determine the percent mass over volume, which is defined as the grams of solute over milliliter solution times 100%. So we know what we're given. We're given grams of solute, which is our 8.46. So it's 8.46 grams of solute, in this case, sodium chloride. And we divide that by the total volume of solution in milliliters, which is our 175 milliliters of our solution times 100%. Gives us then a percent mass over volume of about 4.83% mass over volume of sodium chloride, where we always identify as part of the description of the concentration, we identify what the solute actually is. So that's how we would define, that's how we would label this solution as 4.83% mass over volume sodium chloride prepared by dissolving 8.46 grams sodium chloride in 175 milliliters of total solution volume. For solutions involving liquid solutes, it's very common, as we talked about previously, to define the percent composition with percent volume of volume. And a very common example of a liquid solution prepared by combining two liquids might be an alcoholic beverage, which is composed of a mixture of an alcohol of some type with water. So if an alcoholic beverage is prepared by combining 120 milliliters of alcohol into a total solution volume of 300 milliliters, then the question might be then, what is the percent volume of this beverage? So once again, we have our picture of we're dissolving 120 milliliters of alcohol, combining 120 milliliters of alcohol into enough water to give us a total volume of 300 milliliters. And we want to label this alcoholic beverage with its percent volume of volume. So by definition, percent volume is the volume in milliliters of the solute compared to over the volume of in milliliters of the solution times 100%. So we have our two numbers. So the percent volume is our 120 milliliters of alcohol divided by the total volume of solution times 100%. So our answer then is 120 divided by 300 times 100 give us a percent volume of 40% volume alcohol. So that's how we would label this particular alcoholic beverage as being 40% volume alcohol. For alcoholic beverages, though, it's also common to express its percent volume, not necessarily with that number, but also with what's called its proof. And this comes from a historical sort of definition of how a producer of alcoholic beverages would prove how much alcohol was in their particular product. So in any case, the proof of an alcoholic beverage is simply equal to 2 times its percent volume number, or likewise, a percent volume number is equal to the proof divided by 2. So a pure alcohol with no water at all would have a proof of 200 because it would be 100% volume alcohol. So if we had the same question, we want to ask ourselves, what is the proof of this beverage? So because proof is defined as 2 times the percent volume, therefore proof is going to be 2 times our value, 40%. So then a 40% volume alcoholic mixture solution beverage will be the same as an 80 proof beverage. 2 ways of defining the same solution, either as 80 proof or as 40% volume. So in summary, with percent composition, we introduce percent composition because it's the type of concentration unit you're most likely to find certainly outside of the science laboratory, because it's very commonly used in the food industry, beverage industry, drug industries to indicate the concentration of the solutions, because those industries know, as we know, that they want to label their product with these concentrations because the concentration does have an effect on the properties of that substance, its applications for that substance. So for example, Everclear is labeled with not only its proof, but also its percent volume. Vinegar is labeled with its acidity. Hydrogen peroxide is labeled with its percent. And very relevant nowadays, hand sanitizer is also labeled with percent volume of ethyl alcohol. It's kind of the active ingredient in that particular product. So what's nice about percent composition is it's a relatively simple way of describing the composition of a mixture, of a solution. And it's also very intuitive because the only possible values are 0 to 100%. A lower percent means less concentrated, a higher percent means more concentrated. The problem is, though, is that the reason why we don't continue with percent composition for most of our chemical studies is that it's more difficult to directly compare concentrations of 2 different solutions if those solutions are labeled with simply their percent composition. So as an example, if we have a 3% mass over mass hydrogen peroxide solution, then that describes the amount of hydrogen peroxide per volume of solution. And what we find is that there are, based on that number, about 5 times 10 to the 22nd hydrogen peroxide molecules per liter of solution. And it's this number that's going to help us understand the chemistry of this solution, the behavior of the solution. Whereas a 3% table sugar solution, a sucrose solution, notice the same percent, mass over mass, 3%, but this sugar solution, this 3% sugar solution would only have about 5 times 10 to the 21 sugar molecules per liter solution. So even though they're labeled with the same percent mass over mass, the actual chemistry we expect to be different because, not only because of different substances, but also because we have about 10 times more hydrogen peroxide molecules in this solution as we do in this solution. So there's a little bit of ambiguity in going directly from the percent composition information to the understanding of the chemistry. So that's why in the next lesson, we'll spend a lot more time talking about the second way of quantitatively describing the composition of a solution, and that is usually molarity. Because with molarities, I can directly compare concentrations of 2 different solutions and still understand their behavior accurately.